Okay, so we want to get a sense of how the kinematic equations treat the direction of time. So we're going to do a simple example of an object launched from ground level, but let's go back to the kinematic equations for the vertical direction. So we have dv by dt, or dvy, because it's the vertical component of the velocity that we care about, that's equal to minus g. And so let's isolate the dvy, and that's minus g times dt. And we get to, where we integrate dvy, we get vy, but we have to add an integration constant, so we have a v naught. And then we have a minus g times t here when we integrate this in time. But there's an assumption here, which is that the later time is larger than the earlier time, so that quantity is positive. Right, so there's an assumption here in these kinematic equations that the direction of time is in the positive direction. So let's go back to let's go to the other kinematic equation, right? So the dy by dt is equal to v, which in this case is v naught minus gt. And so we get our y value, right? So we're going to multiply by dt, then we'll integrate dy to get y. We have to add an integration constant. And when we integrate this in time, we get a plus v naught t, and this one we have minus 1/2 gt squared. We're familiar with this. Now let's think about launching this object from ground level at t equals 0 at speed v naught. Right, so those are our conditions. And we want to plot this motion. So let's say, so here is our plot of time. So time is increasing in the positive direction, and this is the y-axis. And at t equals 0, we have the speed of the object is v naught. So maybe let's draw in red. Right, the object is at y equals 0, but it has a speed v naught. So let's just draw the speed of the object there, v naught, and it's upwards. Let's see. Let's find when it reaches its maximum height. Right, we know how to do that. Vy equals 0. Where's our vy? Right here. So when this is 0, v naught minus gt is 0. So at t equals v naught over g, right, this becomes 0, and y is equal to, we start at 0, we have v naught times this t, which is v naught over g, minus 1/2 g times this t squared, which is v naught over g squared, right? And what's that equal to? It's v naught squared over g here, and minus half v naught squared over g. So we get 1/2 v naught squared over g. So this is v naught squared over 2g. That's the maximum height. And we get there at a time v naught over g. So this time is v naught over g. We reach the maximum height. Right. Y goes like negative t squared. Here, this is a parabola. And so we're going up like this. reach the maximum height. We're going to come back down, of course. We can imagine that it's going to be symmetric, so we expect to get this to be twice the time. Let's make sure of that. So we reach ground level when y is equal to 0, and we have v naught t minus 1/2 gt squared, so the t for when the object reaches ground level is in fact 2 v naught over g. So this is 2 v naught over g, and then we have the motion there. And of course, the velocity, the vertical component of the velocity must be downward. So let's make sure of that. What's the vy at that time? It's v naught minus g times t, but our t is 2 v naught over g. So of course this reduces to minus 2 v naught. So overall we get minus v naught. And so we have a velocity vector which has the same magnitude. It's just v naught. Let's draw it out here in red. It's just the opposite of this in terms of direction. Right, so we have object is launched at v naught, it travels upward, the speed becomes 0, then it increases in the negative direction, and it hits the ground with this same speed, but opposite direction, of course. So let's see what happens when we reverse the direction of time. So there's an assumption here that time is increasing in the positive direction. Surely, if that's a fundamental feature of the way the world works, if we reverse the direction of time, we should get nonsense. So let's see if that's in fact the case. So let's start from our kinematic. Let's derive the kinematic equations given this difference, this change in the direction of time. Let's start again with dvy by dt. The acceleration is negative due to gravity, and this brings us to dvy equals minus g dt. But now the dt, right, there's a small increase in that direction, and so the later t is going to be smaller than the earlier t. And so this actually brings in a negative term. So when we integrate and we get vy, we have the constant of integration, vy equals v naught. We have a negative coming in here, so we get a plus gt here. And so vy equals v naught plus gt is the equivalent of this equation before the time reversed situation. And the kinematic equation for y was this. And what is it in this case? Well, we have dy by dt is equal to this, v naught plus gt. And so let's isolate the dy. That gives us v naught plus gt in dt. And now we integrate both sides. This gives us y. All right, we add a constant of integration, of course, plus the v naught integrated in dt. That will give us a negative because the dt again involves that's a negative difference. So we get minus v naught t, and then we have a negative here as well. So we get minus 1/2 gt squared, and that's our kinematic equation for time reversal. So again, we'll imagine the same problem. At t equals 0, we launch an object from ground level at speed v naught. And let's do the same thing. We want to make a plot of the position as a function of time. So this is y, and this is t, but now t is increasing that way. Sorry, t is, the direction of time is to the left. T is decreasing as a result of that because it's becoming more negative. So let's see, we want when the object reaches its maximum height. We know that at t equals 0, here it is. It's being launched upward at a speed v naught, same as the previous, same as this. And let's see, it reaches a 0 speed, so it reaches, sorry, 0 equals v naught plus gt, so our time when the object reaches maximum height with 0 speed is minus v naught over g. So it's not really, perhaps not really surprising that we get something that's symmetric. All right, so at t equals minus v naught over g, we're going to be at the maximum height. So this is minus v naught over g in time. Let's see what the value is for the height. Y equals, we're looking at this equation, right? Starting at 0, we have minus v naught minus v naught times this time, which is minus v naught over g, minus 1/2 times g times this time squared, which is minus v naught over g squared, and that gives us v naught squared over 2g, and so it looks like we're starting to reproduce the same kind of solution that we saw before. This is the same value we found here, v naught squared over 2g. It's just associated with a negative time because time is flowing in the other direction. So this is going like this. It's supposed to be a parabola of some sort there. And it looks like if this is sort of the mirror image of this, then we will get this coming back down. And so in a sense, we take this that we see here, we just flip it about the y-axis to get this. That looks like what we're getting here. And let's in fact confirm this. So now we want the time when the object reaches y equals 0, the ground again. So y equals 0 is the initial value, which is also 0. This is minus v naught t minus 1/2 gt squared. Okay, I can divide by t because I'm looking for a non-zero t here. And of course, t ends up being minus 2 v naught over g, which is in fact twice this value, minus 2 v naught over g, in the same way that this one was twice that value. This is 2 v naught over g, and so it's twice this value. So that's reproduced here. And let's see, we want the speed, which we presume now is going to be downwards, so minus v naught, right? Just like this one is, because it's the mirror image of that. So let's confirm that. Where's our vy? It's right here. So we have v naught plus g times minus 2 v naught over g, right? It's this time that we put into here, and we get v naught. The g's cancel, minus 2 v naught. In fact, we get minus v naught. So if we draw a red, I'm going to end up writing on top of this. Let me just erase this. This is the time. It's just twice that. The vy component is, as expected, it has the same length, but opposite direction. So what can we conclude here is that, in fact, our kinematic equations don't seem to have a problem with changing the direction of time. So let's say, how do we want to write this? The kinematics or kinematic equations don't discriminate against the time direction. Okay, this is a fundamental conclusion that is a little surprising because we'll see this over and over again when we explore other so-called laws of physics, where we reverse the time and we'll get the exact same description.